In our daily lives, hand movements are among the most natural forms of expression, whether in greeting, dancing, or playing instruments, and these actions are often accompanied by rhythm, melody, or resonance. Movement itself already contains the potential for sound. Inspired by this symbiotic relationship between motion and sound, my project explores embodied perception, using the body as a musical interface, where gestures directly generate music and trigger immersive feedback. The central theme of the project is the mushroom, a metaphor for the living rhythms of nature. Its slow yet inevitable growth mirrors the way music accumulates and then bursts forth, serving both as a visual symbol and as a conceptual bridge between movement and sound. By capturing real-time body motion data with sensors, such as the MPU 6050, the system transmits this information to different devices that respond dynamically. The aim of this project is to create a new form of musical expression that connects body, sound, and matter. My project combines sensors, hardware control, and sound design. First, the MPU 6050 6-axis sensor captures the body's movements in space, and this data is processed by the ESP32 while also driving the hardware. The geared motor rotates the gear system, the servo motor moves the rack up and down, and the LED strip changes its colors according to side-to-side motion. At the same time, the 6-axis data from the sensor is transmitted to max/MSP. In the software, this data is mapped onto different sound parameters such as pitch, rhythm, filtering, and spatial effects. For example, the X-axis controls the stereo panning, the Y-axis affects the filter cutoff, and the Z-axis changes the depth of reverb and delay. The gyroscope data adds even more details, such as timbral modulation or triggering looping fragments. Through this design, body movement and sound are combined in real time, transforming physical gestures into musical expression and creating both interactivity and immersion. In evaluating the outcomes of my design, I found that the most effective aspect was how body movements were transformed into immersive sound experiences. The real-time mapping in max/MSP not only controlled pitch, rhythm, and effects, but also used multi-channel audio to reveal the direction of sound in space. For example, when the body moved left or right, the sound shifted accordingly across channels, which made the auditory feedback feel highly intuitive and directly aligned with physical gestures. One limitation I observed was the delay in the servo motor's response, which sometimes disrupted synchronization between motion and the rack's movement. To improve this, I refined the ESP32 control code and applied smoothing strategies in max/MSP, reducing jitter and making the interaction more consistent. Overall, the evaluation showed that the combination of multi-channel sound and motion data created a strong sense of spatial presence, while also highlighting areas for further refinement. This project made me reflect on the idea of embodied perception, how sound is not only heard, but also felt through the body's movement and balance. By mapping gestures into spatialized, dynamic sound, the system creates a sense of presence where action and perception are tightly linked. Looking forward, I plan to extend this into a wearable instrument, allowing performers to carry the interaction into different spaces, with wireless sensors, smoother mapping, and richer sound design. In conclusion, my earlier attempts of directly translating sensor data into sound often produced noise, since the raw values were too chaotic. Through this project, I found that applying effects and smoothing the data flow allowed me to balance musical beauty with the scale of movement. Small gestures could create subtle variations, while larger motions shaped sound in powerful but controlled ways. This approach reveals both the expressive potential of embodied perception and the future possibilities of wearable, movement-based musical instruments.